All right, so just for everyone who's watching or watching this video later, this is the week 9 written homework problems. This is the review session for them. This is stuff about elasticity and Young's modulus, stress, strain, all that type of stuff. A lot of equations, a lot of values and units to keep track of, but it's mostly like mathematical relationships and just kind of plug and chug stuff. So hopefully it shouldn't be too bad. But yeah. Okay, so problem 1 is stretching a rod. It says the figure on the right shows a force versus stretch graph for a 1 meter long rod with a diameter of 4 centimeters, right? So let's write some information down here. We have length of the rod, that's 1 meter, and the diameter is 4 centimeters. And usually that's my bad, diameters, not radius. Diameter is 4 centimeters, so that gives us a radius of 2 centimeters, right? And usually, since with any of these equations you have everything in SI units, so we want to convert this from centimeters to meters, right? So this should be around 0.02 meters then for our radius. And then the rod requires a force of 16 kilonewtons to stretch it by 1 millimeters, which is exactly kind of what we're observing here. 16 kilonewtons to stretch it by 1 millimeter, right? Now, for part A, it's asking us what is the linear stretching spring constant, right? It's linear stretching spring constant. So remember the spring constant from the one that we used in spring potential energy from the last chapter, and the one that we used kind of at the towards the beginning of the semester with F equals kx, right? The spring force. It's K. K is what we're looking for here. That's our spring constant, right? So if you remember, with spring force is F equals negative kx, right? And the negative here comes from the fact that the force, or the spring force, is a restoring force. So if I'm compressing the spring to the right, giving it a positive displacement, right, then the spring force is going to be pointing in the opposite direction in order to restore the spring into its original equilibrium position. That makes sense, right? So if I compress it a positive 4 centimeters, the force is going to be negative, right? Let's say it might be negative 4 newtons or something like that, whatever. And so that just shows that that negative sign is there just to indicate that the spring force is a restoring force, right? So from that little equation here, we have an important relationship that is the spring constant and how it relates to force and displacement, or the length compressed, right? Sometimes you'll see this as negative k, especially in this chapter. You're going to see it as negative k, or at least maybe like k and then delta L, right? So that's like your length of the spring or the object displaced, basically. So if we're trying to figure out K, how can we do that from the graph here? Slope, right? Excellent. So if you take F divided by, yeah, go ahead, Matthew. Not quite, because look at the units here. It's 16 kilonewtons, so this would be 16,000 newtons, right? And this is a millimeter, so we have to convert that to meters to make sure that everything is in SI units and everything is making sense, right? So that way we don't mess up any of our other problems here as well. So we should have F over delta L essentially, right? And that's equal to our K. But yeah, we can take the 16,000 kilonewtons, or 16,000 newtons, my bad, 16,000 newtons, 16 kilonewtons, and divide that by your millimeters, right? So that's 0.001 meters. 1, 2, 3, yep. 1 millimeters to 0.001 meters, and let me calculate that out real quick just to check. You should get, that seems ridiculous, but I'll go with it. 16 million, yeah, I guess, newtons per meter. So they might want us to, maybe it might be just a little bit easier to do it in, what's it called, scientific notation, so 1.6 times 10 to the 7th then, newtons per meter. But yeah. Sound good so far? It's a huge number. Any issues you guys see with that, just want to make sure, because like I said, with this chapter especially, I'm low on confidence. So I just want to make sure that it all kind of adds up and makes sense for you guys, because sometimes, like, if I see a big number, I'm like, all right, there's something wrong. But yeah, looks about right to me, honestly. All right, so this is 1.6 times 10 to the 7 newtons per meter, or essentially 16 million newtons per meter, if you want to write it without scientific notation. So now we have part B, which is what is the Young's modulus of the rod, right? So Young's modulus, if you remember from lecture, is kind of a intrinsic property, right, of the material that we're looking at, right? So for a rod, for a cable, whatever, each object is going to have its own Young's modulus, right? It's going to be characteristic of the object itself, and that's what gives, or what we refer to as, the stiffness of an object. So remember, earlier in the semester we were saying that K, right, the spring constant, if you have a larger spring constant, it means a stiffer spring. And so the reason we say that is because of a relationship between K and Young's modulus, right? So for K, we know that it is equal to, this is an equation from the lecture, it's equal to Young's modulus, which is Y, times the cross-sectional area of the rod or the object that's in question, and then divided by the length of the rod or the length of the object, right? So the idea here is that the Young's modulus, the larger it is, the stiffer the material is. And so obviously, the larger the Young's modulus, the larger the K. And so the Young's modulus is actually kind of the underlying property that kind of determines the stiffness of a spring. So if we say, oh, there's 100 newtons per meter for our spring constant, right, versus 200 newtons per meter, then we know that 200 newton per meter spring constant indicates that the that spring, I guess, with a 200 newtons per meter spring constant is a lot stiffer, right? And so the reason why it's stiffer is that maybe that other spring has a larger Young's modulus, right? Assuming everything else is the exact same. So with that being said, we want to find out the Young's modulus, right? So we can relate it to the spring constant. So if we have the spring constant from part A, which is that 1.6 times 10 to the 7th newtons per meter, right? We can multiply over the length of the rod. That was what, 1 meter, right? And then divide by the area, the cross-sectional area, right? So that gives us our Young's modulus here. So the cross-sectional area, right, if this is just a rod, right, if you think about a rod kind of as a cylinder, then the cross-sectional area, remember the idea of a cross-sectional area is that if we cut this thing in half, what do we observe, right? If we were to just look at the bottom there, if we picked up the rod, snapped it in half, like if you snapped a pencil in half, looked at kind of the inside of the pencil, you kind of see a circle as your cross-sectional area, right? So if you cut the rod in half, right, cut it in half, you see a little circle as the cross-section, right? And so the area for a circle is pi r squared, right? So we take pi and then r, right? Our radius was, well, they said our diameter was 4 centimeters, right? So that gives us a radius of 2 centimeters because the radius is exactly half of the diameter. And then we can convert that to meters, right? Because we want everything in SI units. So we can take 0.02 meters and then square that. And you can do that whole thing and figure out the Young's modulus. Let me grab a more advanced calculator here to make sure what I'm doing is correct. But go ahead and as well let me know what you guys get for that problem, just so we're all kind of checking each other. The A isn't equal to 1. My bad. Yeah, I multiplied the length of the rod over. So here's the spring constant times the length of the rod, and then divided by the cross-sectional area, which is pi r squared. I got around 1.27 times 10 to the 10th for my Young's modulus. I used 3.14 for pi just because I couldn't find my other calculator, my graphing calculator. So I'm just using just a basic like scientific one, and I just put in 3.14. So if you use exactly pi, right, then you might get a slightly more accurate answer, but around 1.27 times 10 to the 10th, which I guess doesn't seem so insane anymore, because usually with Young's modulus, if you remember from lecture, we were dealing with a lot of Young's modulus values that are in the gigapascal region. So I guess this is kind of a sanity check. Looks like what we're doing isn't horrible, right? And this is, yeah, you can say this is all pascals, or you can say newtons per meter squared. Absolutely. I would prefer to put pascals, just because that's the usual unit for it. Newtons per meter squared is kind of like the derived units for it. So it's as if saying, remember, like for newtons are kilograms times meters per second squared. So it's just a lot simpler to put pascals. Saves space, saves time, and it's just less confusing, I guess. Because sometimes you might just put, like, instead of divide, you might say newtons times meters squared. So I would just avoid that and just put the pascals there. But yeah, so I guess we're all in agreement to a certain extent. 1.27 times 10 to the 10th pascals. All right. So now the second part, or the third part, I guess, of this problem is that they're asking us about the stress required to put this rod under a strain of 6%, right? So strain, there's stress and there's strain when it comes to talking about like elasticity and rods and stuff like that, and the restoring force that we have when we're exerting forces on, certain objects. So strain, or actually let me start with stress first. So first of all, we have this equation, F equals kx, right? That's our spring force equation, right? Based on our knowledge from earlier, from part B, we know that really the spring constant is made up of Young's modulus, right? That's the intrinsic value that gives us our quote-unquote stiffness, right? And that's multiplied by the cross-sectional area and divided by our original length of the object or the rod, right? So we started off with that F is equal to kx, right? If we can replace that k with this part right here, we can say that, okay, k is Young's modulus times the area divided by the length of the rod, and then multiplied by x, right? And x, we can refer to that as well as, instead of saying x, like I said before, you're going to see a lot of delta L, right? The change in the length, or the amount of compression that you see or extension that you see with regards to the object or the rod, right? So instead of x, we can just say like delta L, right? So this is all multiplied by delta L. So the concept of stress and strain, right, are just parts of these different, or parts of this equation, essentially, right? So if you think about, this is a really good way about thinking about stress and strain, and how to understand, or I guess how to see them in this equation, is that, remember where you had this old equation here from algebra, y equals mx plus b? So there's components to this equation like there are components to this equation here, right? We have our y, right? That's our y variable. That's going to be the point that we see on the y-axis. That's our y coordinate, right? X is our x coordinate, obviously. M is our slope, right? It tells us how much, we should increase on the x-axis, and then as well to the y-axis, right? So it's a constant that tells us our rise over run, basically, right? So B here, remember, is our y-intercept. So essentially, it's kind of a similar idea here, where there are different components to the equation. You have to recognize each component. So there's going to be a quote-unquote slope. There might be a y-intercept in a sense. Not really, but like I'm just saying that there are components to the equation that we can figure out. And those components are going to be stress and strain. So stress is defined with this little sigma here. And it's defined as force divided by area, right? It isn't necessarily like this. You'll see here later on in the semester that force applied over a specific area is also known as pressure. And this isn't necessarily pressure. At least we don't define it to be as pressure, because pressure implies that the force is applied uniformly to the object. But in this case, when we're looking at, pulling on a rod, stretching, compressing, stuff like that, it's not a uniform force applied over the entire area of the object. So we don't refer to it as pressure. But in terms of the units, it has the same units as pressure. So this is our stress. Once again, this is stress. Now strain is another component of the equation, and it's not sure what this letter is in the Greek alphabet, to be honest, but I'm just not good with I used to know them, but hey, it is whatever. I'll just call this fancy E, fancy small lowercase e, epsilon. There we go. I don't know why I forgot that, but that totally makes sense, right? But yeah, so this is our linear strain, right? And that's going to be equal to the compression, right? The delta L over the length of the rod, the original length of the rod, right? That's our strain, right? Linear strain. And the reason you can think about this as linear strain, at least how you can remember it, is that it relates how much the rod was stretched to the original length of the rod. So if you think about strain as in, okay, how did we strain this rod, right? How did we change or, I guess, quote unquote, put pressure on the rod in a sense, because I don't want to say pressure and confuse it with stress, but how much did we strain the rod by? How did we stretch it, right? How do we compress it? That's why you see the delta L there. Now with stress, think about stress. If you're under a lot of pressure in school, right? You're under a lot of stress. So force over area, those are the units, or at least the same units for pressure, right? Because newtons per meter squared, right? That's going to give us our pascals as well. So that's stress, and this is strain. Strain as in, how are we straining the or stretching or compressing the rod or the object, and stress is how much pressure we're inducing or putting on the object itself. That's the difference between stress and strain, right? So for part C, when they're asking what stress is required to put this rod under a strain of 6%, right? Well, we look at what is the strain. Strain is 6%. 6% is defined as 0.06, right? So we know that component is 0.06 for the strain, or the epsilon L here, right? So with these components, we can use them to rewrite this equation here. And so you can see if we divide over the area, right, we get F over A. That's our stress component. And that's going to equal to Y times our length compressed over the original length of the rod. This is our strain, right? So you can say then that the stress is equal to Young's modulus times the strain that you observe, right? So in that case, if we want to erase all of this work here real quick, just to kind of focus on, or at least, you know what, I'll just move it over. That's going to be better. Oops, I'm trying to select all of this and move it over a little bit. Okay, so here's our stress is equal to Young's modulus times the linear strain. So if our linear strain is 0.06, we want to figure out Young's modulus here, 0.06, and we know Young's modulus is what, 1.27 times 10 to the 10th pascals from part B. So we can say that our stress is equal to 1.27 times 10 to the 10th pascals, and then multiply that by 0.06 for our strain. And then that should give us what the stress is to put the rod under a strain of 6%. So let me calculate that real quick just to make sure that everything checks out. And then let me know what you guys get as well, just so we can be sure. Okay, I got around, that's 762 million, so that's what, 7.62, that's times 10 to the 8th, yep, 10 to the 8th. And that's going to be in pascals, or at least you can say newtons per meter squared as well. For stress, I don't know, I would, really it doesn't matter if you put pascals or if you put newtons per meter squared. It shouldn't matter, at least, because they're same values, the same units at least. But I don't know. I'm not quite sure there if you should have it in pascals or newtons per meter squared. But I would maybe, yeah, that's what I was about to say. Like, it's usually newtons per meter squared on the slide, so I would keep it at that maybe, just to err on the side of caution. So 7.62 times 10 to the 8th newtons per meter squared. But yeah, sound good so far? We're doing pretty well. Your professor used an example using pascals as units. I mean, really, it shouldn't like matter in a sense, because the units are the units. Pascals is defined as newtons per meter squared. It's just that I think commonly pascals are used when you have pressure as the variable that you're kind of looking at. And so this isn't necessarily pressure, because like I said, it's not a force applied uniformly across a area of the object. So I mean, I would say just put newtons per meter squared, because there's absolutely nothing wrong with that. Like, they can't question you if you say newtons per meter squared. So I would just put that newtons per meter squared, just so you're not playing with fire. Yeah, if they gave you, for example, the strain here, and you had Young's modulus, you can figure out the stress, or vice versa. If you had the stress, right, and you had the strain, or if you had the strain and you want to figure out Young's modulus, you can do that. Or if you had the stress and you have Young's modulus, but you want to figure out the strain, you can do that as well. But the idea here is that you have to have a decent amount of the values available here. Otherwise, you're going to have to go to like the more expanded version of this equation here, which, like I said, we started off at F equals Kx, and K was equal to Young's modulus times the area divided by the original length, and then the X was the delta L. So yeah, I mean, unless they give you the strain outright or the stress outright, then you have to use this equation, this expanded one. But yeah. Sound good so far? All right. I'll take that as yes. For part D, now it's asking for how much elastic energy is stored in the rod when it's stretched by an amount delta L is equal to 0.6 millimeters, right? So once again, we hate things that are in millimeters, centimeters, micrometers, all of that. We want to convert things to SI units, right? So if this is 0.6 millimeters, it's going to be 0.0006 meters, I believe, right? Is that 1, 2, 3? Yep. 0.006 meters. And that's our delta L, right? So now it's asking for how much elastic energy, right? So if you remember elastic energy, elastic potential energy, right? That was UEL is equal to, or at least we said, US, but let's use UEL, and that's equal to half kx squared, right? Now, like I said, instead of x, we usually just go with delta L in this chapter, especially because we're looking at the length, because we're referring to lengths usually, not like displacements or stuff like that. So we're just looking at length of the rod, length compressed of the rod. So we use half k delta L squared, right? For the sake of keeping things delta L's and L's, right? Because we have L0, so we want to have things in L's. But we don't want to take L's in this class, right? That's why we're here. So you take half and you multiply by the spring constant, right? The spring constant that we had before was that 1.6 times 10 to the 7th newtons per meter, right? So 1.6 times 10 to the 7th newtons per meter. And then delta L was that 0.006 meters. And then we square that, right? And that should give us our elastic energy stored in the rod. Let me go ahead and calculate that as well. And please do that on your end as well so we can check that we got the right stuff. Physics tutor and a comedian. I try my best to at least well, I don't know. Okay, so I never really go back to check how I sound, but I mean, hearing myself talk right now, maybe I sound a little bit monotone, so maybe my humor comes off as dry as well, but I try my best to make these sessions as interesting as they can be with a maybe not so interesting topic. Let me finish that calculation there. Okay. Yeah, I got 2.88. Yep. Okay, well, I'm glad I'm not monotone either. That's awesome. Yeah, go ahead. Yeah, absolutely. Yeah, you can do that because that's just an expansion of what the spring constant is. Because remember, we said the spring constant was YA over L0, or original length. So you can absolutely take this and plug it in here. But that would just be a lot more values that you have to plug in because you have to put in your Young's modulus, your area, your original length of the rod. But we all know that to be equal to K. So I think K would just be simpler here. But yeah, you can absolutely do it the other way as well, and you get the same answer. Unless you didn't. I don't know. But okay, cool. All right, so I guess everyone's on the same page, 2.88. Awesome. All right, so here's the last part of the problem. How much work is required to stretch the rod further from an extension of 0.6 millimeters to an extension of 1 millimeters, right? So, yeah, it's my bad, 2.88 joules. Yeah, I forgot the units for that. 2.88 joules. Yep, this is elastic energy, so energy should be in joules, right? Now, how much work is required to stretch the rod further from an extension of 0.6 millimeters to an extension of 1 millimeter? So, this is the part where I'm a little unsure about, just to be fully transparent here. But it seems like to me that it would just be a repetition of what we have going on here, except that now the delta L will just be the difference that we have between 1 and 6 millimeters. But let me read this over real quick again, just to be sure that that should be the way we go about this problem. So how much work is required to stretch the rod further from an extension of 0.6 millimeters to an extension of 1 millimeters? Yeah, I think that's just the way to go about it, to be honest. To figure out then what's the amount of energy there at 1 millimeters compression, right? Or extension, actually, my bad. And then essentially subtract it from what's going on here, because that would be the amount of work that would be done to extend it further, basically. Because that would be equal to like the amount of energy that you'd have to add into the system, or do on the system to get it from an extension of 0.6 to an extension of 1 millimeters. So once again, 1 millimeters is 0.001 meters, right? 1, 2, 3, yep, 0.001 meters. So for the elastic energy at 1 millimeters is what? Okay, so we have 1.6 times 10 to the 7th newtons per meter. And then our, not compression, but extension here is at 0.001 meters, and we can square that. And then whatever we get here for the elastic energy, right, we can subtract 2.88 from it, because this value will be inevitably bigger than this value because the extension is a lot bigger, 1 millimeters versus 0.6. And so let me calculate that out, and please calculate on your end as well, just so we're all on the same page. Okay. I got 8, exactly 8 joules for the energy there. But yeah. Well, the displacement here will just be like the extension that we have, the 1 millimeters. And then from what I am seeing, like I said, if I'll look at these problems after the session as well, and if I see anything that should be different, I'll let you guys know. But from what I'm seeing here is that you should just take the energy that would be at that extension and subtract it from the energy at the original extension, that 0.6 millimeters, and that's going to give you the amount of work that you need to do on the system to extend it further, basically from 0.6 to 0.1. So if we take 8 joules, then minus 2.88, that should give us what? 8 minus 2.88 is 5.12, right? 5.12 joules of work. Yeah, it should be 2n extension, an, instead of 2n. But I'm pretty sure that's how we should go about it. Any other ideas you guys have? Like, sometimes like I might just overlook stuff, so is that how you guys went about it too, or at least how you thought about going about it as well? Yep. You can do that as well. Absolutely. Because that would just be you doing like, it'd be saying like, okay, well, delta UEL, UELF minus UELI, right? And so then you can just take half K, like delta LF minus, well, LF minus LI, and then square that. Yep, you can do the same thing. But yeah. Does that sound good so far? I think that should be how we should go about it. At least I sincerely hope that's the case. Yeah, one sec. So if we do, okay, 1 minus 0.6, that's a, that'd be 0.4 millimeters, right? And that's 0.0004 meters. 1, 2, 3, yep. And if we square that, multiply by the spring constant, at least it should give you the same. I don't see why it shouldn't. Therefore, and square that. Oh, you do get a different, you get a different answer. Okay. So, all right, so let me look at this one more time, because then that just throws things out the window there. So, yeah, around 1.28 is what you would have gotten if you did that. Now, I think it's the problem with just how we're defining things. So, okay, I see why. Okay, I don't think you can do then like LF minus LI. Okay, yeah, I don't think you can do that necessarily. And I think maybe the reason why, at least, okay, so like I said, I'm just not 100% sure about this, but if we go back to what we defined delta L to be, and delta L is the distance that we compress or stretch a specific object or rod, right? So we initially extended it to 0.6, and then we want to extend it further to 1 millimeter, right? Now, if you were to do 1 minus 0.6, right, that gives you 0.4 millimeters, and that's 0.004 meters. If we were to plug that into the equation, right, and solve for what the elastic energy is, I believe that would just give us the elastic energy at 0.4 millimeters, right? It wouldn't give us the difference in energies between the two different positions or the work that we would need to do to, move it from 0.6 to 1 millimeters. So, yeah, I mean, I think it would, yeah, you based on the definition of delta L being, the distance that you compress or stretch an object, I don't think you would just be able to do LF minus LI, because like I said, whatever this is, right, this would be the 0.004 meters. That would just tell you what the elastic energy is at that distance, which would be, when we said that's 0.4 millimeters. So that would tell us what the elastic energy is at an extension of 0.4 millimeters, right? Which is like not as extended as 0.6 or 1, right? So we're trying to figure out, like, okay, here's 0.6, here is 1 millimeter, here's 0.6 millimeters, here's 1. We're trying to figure out, okay, well, here's a certain amount of joules that we get to, so this is our equilibrium position, right? Here's the rest of the spring, right? So to go from 0 to 0.6, that took us, what was that? The 2.88 joules, right? 2.88 joules to get us from 0 to 0.6. From 0.6 to 1, or at least not 0.6 to 1, but from 0 to 1, it took 8 joules. In order to go from 0.6 millimeters to 1 millimeters, it's the difference between these two. It's the extra amount of energy that I have to put in to get from 0.6 to 0.1, or to 1, right? So that would be that 5.12 joules that we got. Now, if we did 1 millimeter minus 0.6 and we got 0.4 millimeters and plugged that into the equation and stuff, that would give us the energy at 0.4 millimeters, which is not what we want. So, yeah, I mean, since yeah, the relationship isn't like linear here. So, but it's not just that in fact it's linear or not linear. It's the idea that that isn't um, that's a I guess, understanding of the definition of what delta L is, and that's the distance that you compress or stretch the spring by. And so, if we define delta L to be 0.4 millimeters, well, that tells us that, okay, if we plug 0.4 millimeters in here, we're trying to figure out the elastic potential energy at 0.4 millimeters. However, if we do the difference between, or at least the difference in energies, right? So we can take what the energy is at 1, what the energy is at 0.6, subtract the two, and find that little, amount of work that you have to do, which is 5.12 joules that you have to add into the system to get it to that 8 joules, right? So I think that's the idea there for part E. So I would avoid just subtracting um, the distances. Does that make sense? But that was a excellent question that should clear up maybe a common mistake that people might have made. But that's what I'm seeing here so far. That's what makes sense to me. Like I said, if I figure something else out, or if I, go back and, see that I did something wrong, I'll let you guys know. But yeah, should be 5.12 joules, I believe. All right, so that should be problem 1 for stretching a rod. That wasn't too bad, right? Problem 2 is bending coefficient. Consider 2 rods that are made of the same material, so they have the same Young's modulus and are of the same length. So they have the same length, same Young's modulus, so the same properties, right, and stuff. But the radius of one is 3 times the radius of the other one, right? So one of them has 3 times the radius of the other one. Okay, well, part A is asking us what is the ratio of the linear stretching spring constant of the 2 rods, K1 divided by K2. What's the ratio between them, right? Now, we know that K, we define that as Young's modulus times the cross-sectional area divided by the original length, right? Well, here's K1. How about K2? Are the Y's going to be the same or different? Are the Young's modulus going to be the same or different? Yep, exactly. So if you look at the Young's modulus should be the same, L0 should be the same between both, right? And so the only difference, like Matthew said, is that the radius of one is going to be 3 times the radius of the second rod. So if you look at the area, right, we're looking at rods, right? So remember I said the rod here, cross-sectional area would be, if you cut it in half, you see a circle, so the area should be pi r squared. So the area here should be pi, right? And R1 is equal to 3R2. So 3R2, and then that whole thing is squared. Now, for K2, we have same Young's modulus divided by that same length, pi R2 squared, right? Now, if you divide the two, K1 divided by K2, then you can see that, okay, we have one second. So radius of one is 3 times the radius of the second. I think I have it right? It should be, so this is the first, so we're defining this as the first rod, right? Then the first rod should have a radius that's 3 times the length of the second one, and here's the second one, right? Unless I'm going full stupid mode on this. Okay, cool. All right, 1 second here, I just have to adjust something on my desk because the lights keep turning off. I think I just have a cable in the wrong place that got pushed over. Sorry about that. All right. So, yeah. If we want to compare now K1 over K2, then we see that for K1, we have, what is it, y pi, and I'll expand this actually just to get it over with from the beginning. If we expand that 3r2 squared, we should get 3 squared is 9, right? Times the y, the Young's modulus, times pi, and then r2 squared. And then that's over your original length, right? And then the other one is just y pi r2 squared over the original length, right? And so you can see here, if you just flip this over and do your mathematical manipulation, I'm just going through this like very intricately and step by step. So we can see that 9y pi r2 squared over the original length. If we divide by this whole like fraction here, it flips things over. So we can see that it'd actually be like saying times the original length and then divided by another y pi r2 squared, right? So you can see there, this cancels out with this, that. And so you can see then that K1 divided by K2 should just leave you with 9. And so the ratio would just be 9:1. Sound good? If you got 1/9, then you might have done K2 divided by K1, but okay, hold up. Let me check if you guys got that. Christian got that as well, so let me check my math here to make sure that everything is in order. So this is K1. We took that and divided by K2. This should flip over here. So you're multiplying by L0 divided by that. Yeah, okay. I'm getting 9:1. Yeah, go ahead. Sorry. Yeah, for K1, instead of saying like, okay, well, R1 squared, well, R1 is equal to 3R2. So instead of saying R1, I plugged in 3R2. Yep, no problem. Alrighty. So yeah, 9:1 should be K1 to K2. Now, part B, very, very similar, but it's now the bending coefficient. So, for bending coefficient, it's another new equation that we have to keep track of again, right? So, bending coefficient, if you remember from lecture, is BC pi over 4, and then multiplied by Young's modulus, and then times the radius to the 4th power, right? That's our bending coefficient. Now, very, very similar, if we define BC1, right, we have same pi over 4 over the Young's modulus, and then R1 is equal to 3R2. So we can just say 3R2 to the 4th, and then BC2 is pi over 4 y times just R2 to the 4th, right? Really, if you wanted to, instead of doing all this division and stuff and you want to skip it over really quickly, at least in terms of understanding what's going on, you can see here that, okay, well, R2 to the 4th is going to be the same as R2 to the 4th. Pi over 4 is the same as pi over 4. Y is the same as y, right? If we just take 3 to the 4th, right? 3 to the 4th, that's 3 times 3 times 3. Oops, what am I doing there? Times 3, right? That's 9 times 9, that's 81, right? So if you pretty much bring that 81 outside, you should get like 81 times all of that stuff there, and you have all of this stuff here. and this would just be 1 times all of this stuff, right? And all of this stuff I'm just referring to pi over 4 times y times r squared, or r2 to the 4th, right? So all of this stuff here is here, and it's just, there's only one of it. As opposed to when you do 3r2, you take 3 to the 4th, that's 81. So it would be like saying 81 times all of this stuff here, all of this junk, right? And if you were to, just go ahead and say that, right? And then you can just see that, well, 81 pi over 4 y 3, or my bad, not 3, r2 to the 4th. And then here it's just pi over 4 y r2 to the 4th. So you can see that this is the stuff that I was talking about. And this is 1 here, basically. They're just saying, like, there's only one of it. Now here's 81 units of this stuff. That's essentially what's going on here. And so if you wanted to go ahead and expand it out, right, and write it formally, and I would do it just so, you're doing the right stuff and you're getting the points and everything. It's better to be thorough than to take shortcuts. So if you just do BC1 over BC2, right, and you say, okay, well, this is 81 pi over 4 y r2 to the 4th, and then this is pi over 4 y r2 to the 4th, and you can just like say that all of this stuff cancels out like this, right, and you're just left with 81. So that should be the ratio of the bending coefficients there. And so just going back to just kind of teaching a little bit, now bending coefficient is another type of unit or measurement, right, or value that describes how stiff an object is, right? So remember, we have this Young's modulus here. So the larger this Young's modulus, right, the larger the Young's modulus, right, then we have a stiffer object, right, or stiffer spring, for example, or stiffer rod, right? So remember, the Young's modulus was also related to the spring constant. So remember, we said larger spring constant equals stiffer, right? That's because there's a larger Young's modulus. Okay, well, if we have this Young's modulus here and the bending coefficient, larger Young's modulus, we'll have a larger bending coefficient, and the bending coefficient is another description of how stiff an object or a rod is, right? So bending coefficient, Young's modulus, and spring constant are all kind of measurements or values that describe stiffness of an object, right? Young's modulus is the deep down underlying property that defines stiffness, and then like spring constant and bending coefficient are like more overarching concepts that, define stiffness. But for bending coefficient as well, the units are newtons times meter squared, not newtons divided by meter squared. So it should be newtons times meter squared for the bending coefficient, right? And newtons times meter squared, you can also write that as joules times meters, right? So those are the SI units for bending coefficient as well. Probably the most annoying thing in this chapter is not even like keeping track of the equations, because you're going to get an equation sheet anyway on the exam. It's just honestly remembering what units go with what values. So we know that spring constant is newtons per meter, right? And for Young's modulus, right, that's going to be in pascals usually, right, or newtons per meter squared. So if we want to write this at the top here, spring constant is newtons per meter. Young's modulus is newtons per meter squared, or pascals as well, right? Bending coefficient is newtons times meter squared, or joules times meters. And let me see, am I missing anything else? I think that's it. Yeah, I think that's it so far. But that's probably the one thing that you should watch out for and keep a lookout for as well, because I mean, usually they do a pretty good job, the professors, about telling you like what units to use. I remember, like, if you guys remember from the exam, like, at least, I mean, I didn't take the exam, so I haven't looked at it in a while, but from what you guys remember, and especially for the quizzes too, like, don't they do a good job about like telling you like, okay, like give me the value in newtons, or give me the value in joules or something like that, right? Unless it's like super obvious, like if you've been doing energy for a week, like what else would the energy be other than joules? Do they do a pretty good job about that, like telling you what units to use, like especially for stuff like this? There's a lot. Yeah, I mean, I think they do a decent job with that. Yeah, just yeah, especially watch out for conversions, because I feel like everything needs to be in meters because of SI units, but if you look at a rod and you're trying to compress like a steel rod, unless you're like the Hulk, you're not gonna be compressing it very far, or stretching it very far for that matter. So like your stretches and compressions are usually gonna be in the millimeter range, and so you're just gonna have to really watch out for converting from millimeters to meters, and stuff like that. But um, I don't have like a mnemonic or any memory like device to use to remember the unit conversions and stuff. I just like I kept looking at them for so long, and I can say them very quickly, and I know like the values and stuff. But other than that, like I don't know. Like I don't know if sometimes I use mnemonics and stuff and acronyms, but I just know it is deci, centi, milli, micro, nano, pico. So deci, centi, milli, micro, nano, pico, right? And so that goes 10 to the negative 1, 10 to the negative 2. So you count 1, 2, and then you go to milli, which is 10 negative 3. So once you get to 3, so you are increasing by increments of 1, 1, 2, 3. And then after that increases with increments of 3. So you go 10 to the negative 6, 10 to the negative 9, 10 to the negative 12. And I believe femto is the last one, which is 10 to the negative 15. So 1, 2, 3, 6, 9, 12, 15. Or 1, 2, 3, 6, 9, 12, because usually femto is not very common. So deci, centi, milli, micro, nano, pico, 1, 2, 3, 6, 9, 12. And this is centimeters, millimeters, micrometers, nanometers, and picometers. 1, 2, 3, then 6, 9, 12. 1, 2, 3, 6, 9, 12. And there's bound to be something online. Like if you, since I'm considering most of you guys are like pre-health something, right? Pre-med or, pre-dentistry or something, right? If you just go to like a Reddit page for, I don't know, like r/pre-med or something, you're bound to find, a couple people with different mnemonics or acronyms for what DC, MM, and P is. There's bound to be something probably hilarious or funny to use to remember that. But I just say deci, centi, milli, micro, nano, pico, 1, 2, 3, 6, 9, 12. There. That's just me. But yeah, I don't know. Anyway, that's problem 2. Problem 3 now is where I just want to like die for like 5 minutes or something, because these are the type of problems like remind me of stuff like on the MCAT, because it's just they want to like test you on physics knowledge, but they relate it to something where you'd never like use in I guess like it's just ridiculous, because I mean, unless you're like really like in depth and stuff, I just don't see the necessity of looking at bending coefficient and all this stuff with DNA when we're like, most of us are like on a pre-med track and not necessarily, at least maybe going to like a super like research based program, or become like it's an insane physician scientist. Well, I mean, at least, I mean, if you're into that super thing, I don't want to discount it. I don't want to discourage you from going to something like that. But like some of these problems, man, like just solely as an undergrad, they make me want to die. But yeah, it's better to know more than to not. So, anyway, yeah, like and the problem is like I'm just going on a rant at this point, because like I've never heard of what this is. So like I would at least like to like maybe have it be relevant to what I'm learning, and be like, okay, that makes sense. Because here's the thing: once you get to like the larger tests and stuff, and all that, you're gonna like get examples, especially on the MCAT and these larger exams, that will seem outlandish, but they actually make sense, and they never really emphasize it. So like I remember for physics 132, you guys learn about circuits, and electricity and stuff, and so the heart acts as a circuit. We never did a single problem about the heart, acting as a circuit, and nothing about the electricity in the heart, anything like that, which is extremely relevant. There's a whole field called electrophysiology about it, and we did nothing relevant to medicine for that chapter. Now, all I'm getting for that, for those types of example problems on like MCAT practice and stuff like that, is I'm just seeing all stuff about how the heart acts as a circuit. And I'm like really just struggling to relate that right now, because it's just like I have to go back and relearn this stuff in a medical context to make sure that it kind of like makes sense and adds up. But anyway, remember IHD from organic chemistry. I don't want to hear about organic chemistry in this chat. All right, zip it and delete, because I don't want to remember orgo, because I took orgo and physics together, and that's why I say I want to die. All right, that's it's a decent refresher, I guess, a break from what was going on. So this ought to be fun for those who are watching on YouTube. All right. Okay, integration host factor, IHF, is an architectural protein in E. coli that helps to package the DNA inside the cell, as well as to organize the DNA for higher order nucleoprotein complexes. IHF can bend some DNA segments that are 35 base pairs long, into a U-turn, as shown in the as shown in the figure to the right. The Young's modulus of DNA is 300 megapascals, and its cross-sectional radius, okay, is 1 nanometer. Model DNA as a cylindrical rod. Okay, cool. So we have DNA segments 35 base pairs long. Young's modulus is 300 megapascals. Radius is 1 nanometer, and once again we'd have to convert that to meters, which is bogus. And then we're just gonna go about parts A through F here real quick. So for what is the bending coefficient, right? So remember from the last problem, we said the bending coefficient was what? Bending coefficient is pi over 4 times Young's modulus times the radius to the 4th, right? So pi over 4 times Young's modulus, which is 300 megapascals, right? And we have to convert that to pascals, right? So actually now I have to this is where I forget stuff. So I know my units downwards. I forget them when I go upwards. So there's kilometers, right? That would be like 10 to the third. Then I want to say, what is it? Is that mega that's 10 to the 5th? I don't remember. Shoot, no, that's not it. 10 to the 6th, that's what it is. And then giga is 10 to the 9th, I believe. Yeah, that's the one. Dope. All right. Is Terra is 10 to the 12th? Just that's what it is. That's what I was thinking of. Terra is 10 to the 12th, I'm pretty sure. Anyway, so for our megapascals, right, we can just multiply that 300 times 10 to the 6th, right? Pascals, and then times the radius, right? That was 1 nanometer. So that's 1 times 10 to the 10 to the 9th, 10 to the negative 9th meters, right? Deci, centi, milli, micro, nano, 1, 2, 3, 6, 9. Yep. And that's to the 4th. And then that's how we can get our bending coefficient. And let me calculate that out. And please do so on your end as well. I made a mistake real quick. 1 second. Okay. I got 2.3355 times 10 to the negative 28. Yeah, 2.36 times 10 to the negative 28. Yep, that's what I got as well. But yeah. Oh, they want us, yep, they said, do they want us, it's joules per meter, yep. Or not per meter, joules times meter, sorry. There. Joules times meters. So, that should be it for part A, right? That's our bending coefficient for DNA. Now for part B, how long is a 35 base pair long segment of DNA? So, I want to express our answer in nanometers, given that the separation between the base pairs in double-stranded DNA is 0.34, right? So this is actually really simple. There's absolutely no physics involved in this. If each, like the separation between each base pair, so that's 0.34 nanometers, right? If there's 35 of these bad boys, right, what do we do? No, you don't have to add the diameter. Yep, exactly. So 35 times 0.34, and they want it in nanometers, thank God. So we're good there, right? Let me calculate that out as well. 35 times 0.34, and that should be 11.9 nanometers, I believe. That's how long the segment is, just from there to there, 35 base pairs. We're not looking at the diameter or anything like that. Part C, they're saying, okay, well, by what angle in radians is the DNA bent in the IHF bound complex, right? So, for the angle that it's bent, all right, so think about that real quick. Doesn't the diameter also take up space in the DNA? So I guess what you're saying is like, oh, I see what you mean. So like, if you have like this double helix here, right? So distance between these two base pairs, you mean? Because I mean, what they're asking about is that for each pair there, right, then we're just looking at the separation distance, and that's what we're trying to figure out, just the total length of the segment of DNA. Mm-hmm. Mm-hmm. So, okay, hold up. I don't know. Like you said it perfectly, and I should understand it, but for some reason I just got like totally confused. So, okay, like if we're looking at this section here, right? So can you repeat once again when you said it? My bad. Mm-hmm. Mm-hmm. Well, the length of what they're saying, like, so, like, remember, we want to model this as a rod, right? So if this is a rod like this, and we can just imagine like the double helix kind of going like that, this, whatever, right? So if you're saying like the radius is like what is it, 1 nanometer or something, right? And you want to figure out the diameter, well, that would give us like the length of the cross sectional area, but not the length of the entire segment of the DNA. And so the length of the entire segment would just be like each base pair, right? Like these here, and then just find like that. Yeah. Yeah. Yep. Mm-hmm. But yeah. Let's see here. So for C, it's saying what angle and radius is the DNA bent in the IHF bound complex. Do you have another question, Jonathan? My bad. That was it. Okay, cool. So okay, hold up. So it's units U-turn. Okay. So yeah. Mm-hmm. I think it would be 180 degrees, but the thing is here, so if we have okay. Yeah. That makes sense. Mm-hmm. It would be so since because it is a U shape, then it would be kind of like a half circle, and a half circle is 180 degrees. Yep. That makes sense. Mm-hmm. So that U-turn like that would be exactly half of a circle, and that's 180 degrees out of 360. Yep. Mm-hmm. That's the one. I think this is kind of bogus though, because it's very implicit. Because if you just like read over this, this is what I did. Maybe you guys got it quicker than I did, so that's awesome. But I think normally what you would probably see is then they might tell you that it bends at, they might say like, let me say pi radians or something like that, and so then you wouldn't even have to do this step, and they would just jump to part D, and you'd have to figure out the radius of curvature. But yeah, since it's a U-turn, right? It's half a circle, and that's 180 degrees. So 180 degrees, 360 degrees is 2 pi radians, right? So it should be just pi radians. But yeah, that's part C. Now part D is what I was talking about, where normally they would just give you what the angle is, and then you can just jump immediately to part D. I think I remember a problem like this on our online homework, and I think the difference was that they gave us the angle in radians, and then you just part C wasn't even a step. Part D is we just jumped immediately to part D. But I think it's better to have part C, honestly, because then you would get more points essentially for like every single step of the problem. I got 180 degrees because they said the integration host factor can bend some DNA segments into a U-turn. And so if you think about a U-turn, right, it's exactly half of a circle basically. So half of a circle of an entire circle is 360 degrees. Half of it is 180. And so then we just convert 180 degrees to radians. There are 2 pi radians in 360 degrees. Does that make sense? Okay, awesome. So we have pi radians, right? Now we have the equation here for radius of curvature. And so equation for radius of curvature is the original length of the rod times the radius, or not, my bad, the angle in radians, and then times the radius of curvature. There. And so the original length of the rod, that would just be the length of DNA, right? the entire length of DNA. So we take that 11.9 nanometers, and thankfully they want us in nanometers as well for the radius of curvature. That's good. And then this is pi radians, and then we can solve for our radius of curvature that way. So that's not too bad, right? You just take 11.9 divided by pi radians. And I think should get around, what is it, 3.79 nanometers or so? Is that about what you guys got? Yeah, that works as well. 3.79, 3.8, either way. The good thing about this class is that there's no sig figs. If we had sig figs, I would have failed this class, because that'd just be one extra thing that you have to worry about for the entire exam. Whoever invented sig figs needs to, like, who hurt them? I don't know why sig figs are a thing. I mean, I know, like, at least I've memorized why they're a thing, but it's absolutely ridiculous. Hey everyone, this is me editing in post. Sorry I made a mistake for part E. Part F is fine. Part E, the issue with it was, for those who attended this session, I merely just calculated for a KBT, right? However, the problem is asking you to calculate the energy required to bend the DNA when T is equal to 300 Kelvin in terms or in units of KBT. So I just completely overlooked what the overarching issue of the problem was, as opposed to just, looking at KBT here. Anyway, here they're asking you for the bending energy. And remember what I said earlier, or at least for those who are watching and who are going to be watching the video, and for those who attended the session earlier, I later said for part F that the bending energy is equal to our elastic potential energy here. So bending energy here is equal to the elastic potential energy. And so that bending energy here is not just going to be KBT for this problem. It's going to be some multiple of KBT. It might be like 4 times KBT or 5 times KBT or something like that, right? Here in part F, they're only giving us the elastic potential energy or the bending energy as KBT and not a multiple of KBT. So that's why part F, actually, there's no problem with it. It's just that there's an issue with part E. So in order to figure out the bending energy, right, the energy required to bend the DNA, or the elastic potential energy, we have to calculate UEL, right? And that's equal to 1/2 times the bending coefficient divided by the original length of the DNA, and then times theta squared, right? So they gave us, or we figured out theta as 180 degrees earlier in the problem, or in one of these other parts here. Yeah, so part C, we figured out that it was a U shape, right? And that was 180 degrees, or pi radians. So we take 1/2 times our bending coefficient, which was 2.36 times 10 to the negative 28 joule meters. 2.36 times 10 to the negative 28 joule times meters, divided by the original length, which was 11.9 times 10 to the negative 9 meters, and then times pi radians, and then square that. And then you should get, for this, I believe you should get around 9.79 times 10 to the negative 20 joules, right? And then we're going to have to take what this energy is and calculate it in terms of units of KBT, right? So KBT is going to give us a energy value as well, right? It's still going to give us an energy value. It's just that now we have to calculate, like, how many KBTs is 9.79 times 10 to the negative 20 joules. So we take 9.79 times 10 to the negative 20 joules and multiply it by how many joules are in 1 KBT. So 1 KBT, right, is equal to, we figured it out in part F, and that was if you take the Boltzmann's constant, which is 1.38 times 10 to the negative 23rd joules per Kelvin, multiply it by 300 Kelvin, you should get 4.14 times 10 to the negative 21, right? So this is 4.14 times 10 to the negative 21 joules. If you divide these two values together, you should get around 23.64. So it's 23.64 KBTs, or KBT units, essentially. That's what the problem is asking for. 23.64 is your answer for part E. So I apologize for the mistake again. I'll add this to the, or this is going to be added, obviously, as you can see here, to the video. And I'll just I'm cutting out the mistake that I made for this problem when it was done live. And then what you'll see here is afterwards, I'll just continue on to part F. So thanks and sorry again for that problem. Now for part F, it says the interactions between the IHF protein and the DNA keep the DNA bent in this U shape. If the protein were to be removed, the DNA would mostly straighten out and bend only slightly as a result of its thermal energy. Now, that would be around kBt. In this case, by how much would this piece of DNA be bent? So this one kind of threw me for a loop when I looked at it for the first time, and I want to say, so here the key is that the DNA would mostly straighten out. So it's only bending slightly. It's not 100% straight, right? Now, we're trying to figure out how much this DNA would be bent, and that's the angle, right? The angle at which it would be bent, and that's in degrees is what we're trying to figure it out in, right? So we know that the energy needed to keep it in that position, right, would be kBt. That's the energy needed to keep in that position. So energy would be equal to kBt. Now, the energy required, right, for bending stuff, or at least when we think about bending and energy, you can think about elastic potential energy. And so there's actually another equation out of the millions of equations in this chapter. UEL is equal to half times the bending coefficient divided by the original length of the DNA times the angle over which the DNA is bent or curved, right? And so our energy here has to be equal to the elastic potential energy. So whatever this is, which is what we got here, we set it equal to the elastic potential energy and then solve basically for theta. And then that'll be in radians, right? Because the normal units here, the theta is in radians for all of these types of problems. And so we'd have to go then from radians to degrees via the conversion factor. So if we have 4.14 times 10 to the negative 21 joules, and we set that equal to half times the bending coefficient, well, we said the bending coefficient was what? 2.36 times 10 to the negative 28 joules meters. Joule meters divided by the length, the original length, right? That was 11.9 nanometers, so we have to convert that as well. So 11.9 nanometers, well, that's 11.9 times 10 to the negative 9 meters. And then theta squared, right? And then we can solve what theta is. So this is a hefty calculation. I'm going to do it here real quick, and then let me know what you guys get as well. Okay. Let's see here. 6. Right, okay, that's degrees. Okay, I absolutely butchered this calculation. I should try and find my graphing calculator somewhere. I'm trying to do this on a scientific calculator and it's not it. But Christian got 37 degrees. I am going to take his word for it for now. 1 second, let me try and find the stupid calculator. Whoa, a number in the millions? That's not good. Okay, it seems like the consensus is 37 degrees. I think mine is slightly off. I got like 36 or something, but so that is the length of the DNA. That's 11.9 nanometers, and so nanometers are, so if you do 11.9 times 10 to the negative 9, well, 1 nanometer is equal to 10 to the negative 9 meters. So 11.9. Yeah, go ahead. So I just do it like this. So I know that a nanometer is 10 to the negative 9 meters. So I take, okay, well, 1 nanometer is 10 to the negative 9 meters. And so I multiply by 10 to the negative 9. So my nanometers cancel out and I'm left with meters on the top. Wow. Okay. Let me look this over real quick again and just double check that I'm not doing anything wrong. Give me 1 second. Okay, 4.14 times 10 to the negative 21 times 2. Yeah, I think I'm still getting 37, around 37 degrees, but I'm not sure exactly where you might be going wrong. Yep, that's the same thing. Because if you just move over the decimal point, it should be 1.19 times 10 to the negative 8. That's the same thing as well. But everybody else got around 37 right from the work that I'm showing here, right? Yeah. It's around 37 degrees. Yeah. Yeah, I guess I'm not sure what is going on. No, well, okay, so yeah, I mean, if you want, you can. What I usually do is that I take the radians that I have, and then I multiply. That's 2 pi radians, 360 degrees, like that. So the reason why E and UEL are equal to each other again is because the elastic potential energy here is also defined as the energy of bending. And so if this is the amount of energy that they require us to keep that DNA bent only slightly, then E should be equal to UEL in terms of that UEL is equal to the energy of bending. And so the energy of bending, they defined it as KBT. Yep. I think that's probably it for this problem. Unless, I mean, so far the consensus is 37 degrees. I'm not sure, Matthew, where you might be going wrong. But I'm just gonna keep double checking just to be sure because, like I said, I'm just not confident in myself tonight. So, I just want to make sure that everyone is on the same page. Okay, awesome. All right. All right, well, if everyone got 37 degrees. Oh, okay, so one person's still getting a different calculation here, so. All right, well, we can walk it through. All right, so if we have 4.14 times 10 to the negative 21, if we multiply over 2, that should give us what, 8.28 times 10 to the negative 21 joules, right? And that's equal to 2.36 times 10 to the negative 28 over 11.9 times 10 to the negative 9th, right? We can then multiply this over here, right? So we have, what is it? We can multiply 8.28 by 11.9. It's like 98. This is going to be huge, but just because, like I said, I've looked everywhere in my room for my freaking graphing calculator. I can't find it. So 98.53 roughly times 10 to the negative 21 times 10 to the negative 9th. Roughly. I think that's what it should be, 8.28 times 11.9. Yep, 98.532 times 10 to the negative 21 times 10 to the negative 9th. And then that should be equal to 2.36 times negative 28. And then that's times our theta squared. So if we want to simplify this real quick, when you multiply these two together, you can add the exponents. right? So this should be 98.53 times 10 to the negative 30, yeah, 30, right? And then you can, once again, just divide over this stuff here, 2.36 times 10 to the negative 28. So I'll divide 98.53 by 2.36 first. 98.53 divided by 2.36, that's 41.75. So I get 41.75, and then 10 to the negative 30 divided by 10 to the negative 28. That should just be subtracting the exponent, so negative 30 minus negative 28, right? That's going to give us times 10 to the negative 2. I believe this is all like just going by math that should make sense, and hopefully I'm not making any mistakes. And then we just really just take the square root of that. And so it should be 0.4175 square root of it. Right? That should give us like 0.646, I think. And that's degrees. And then we can multiply 360 degrees by 2 pi radians like that. Hold up. Did I screw something up? Because now I'm getting, now I'm not getting 37 degrees. Okay, this should not be this hard. If I had my graphing calculator, I'd be done with already. Yeah, I multiplied by 1/2. I multiplied it over at the beginning. Yeah. Well, now I'm just not sure anymore. Okay, hold up. So Eric just said that he multiplied 0.646 by 360 and then divided by 2 pi. And you can, yeah, I mean, well, in this case, so if I'm getting degrees here, right, if I'm getting 0.646 degrees, well, then there are 2 pi radians in 360 degrees. Okay. So the degrees should cancel. So it should be 2 multiplied by 2 pi and then divide by 360. I'm fairly certain. It shouldn't be the other way around. But that just gives you an answer that's very, very strange. So if you multiply by 360 and divide by 2 pi, that's where everyone got 37. But I got, just by doing it again here, .0113. Yeah, 0.0113 radians. Or my bad, the other way. Oh no, okay. Now I see what. Okay, all right. May God have mercy on my soul. My goofy little self forgot that this problem from the begin with even gives you radians. It should be, yes, okay. It's 0.646 radians, not degrees. And then that's 2 pi radians, 360 degrees. Okay, thank God. Now that's 37. I made the mistake of saying that 0.646 is what you get, and that's in degrees, and it should be in radians. Whatever you get here is in radians. And then you divide by 2 pi radians and multiply by 360 degrees. That's the mistake I made. Now you should get 37. Does that clear it up for everyone who's getting a slightly different, well, I guess not everyone, because everyone seemed to be on the right page except me. And yeah, you can also do 180 divided by pi as well. Really just any ratio that's on the unit circle. But yeah, my bad. See, I went through the whole homework without making any major mistakes, and then I screwed up the very, very last problem. But 37 degrees is what you should get. It's 0.646 radians, and it's 37 degrees, roughly. So that's it for problem 3. It's wasn't horrible, I guess, but I just don't like these types of problems where like they give you like one piece of information that relates it to anything remotely like scientific, or at least not scientific, at least like medical in a sense. But I would much rather have a problem that's like actual, like you know how like we did the torque problems, we did that like with muscles and stuff, like that's why it was interesting, and that kind of made sense to me as to why it's important to like lift things a certain way and like moment arm and stuff like that. Anyway, but yeah, not a fan of this problem, but it is what it is. But hopefully that cleared things up for this written homework and explained some of the things along the way with regards to like bending coefficients, stretching, compressing rods, how to calculate for all this stuff, the relationships between the spring force and displacement, and all that stuff. So and hopefully it helps you understand as well like the concept of Young's modulus, bending coefficient, and how they're like measurements or descriptors of like stiffness in an object. But that's been it for this written homework review. We have 7 minutes left. I'm not sure if we have time to like go over any of the online, but we have a question here. So part E of question 3, why again was the energy equal to the elastic potential energy? So elastic potential energy, that would be defined as your energy of bending. And the reason why is that you can see here, it integrates the bending coefficient, right? So elastic potential energy is also defined as the energy of bending. And so they told us if the protein were to be removed, the DNA would mostly straighten out and bend only slightly. And the energy at which that bending would occur would be kBt. So the energy, right, kBt, to provide the bending is also equal to the elastic potential energy, because elastic potential energy is the bending energy. So if the bending energy is kBt, then the elastic potential energy is kBt. And so, and just for those who are watching online as well, we got this little section here by taking whatever we got for part E. So it'd just be 4.14 times 10 to the negative 21, which is the Boltzmann's constant times the temperature. And yeah, so when they ask us for the energy required to bend, energy required to bend is the elastic potential energy. Because think about it, like, because remember for the last week's stuff with spring potential energy, which is the same as elastic potential energy, think about like the amount of energy it takes to compress the spring is the amount of energy like bending as well, right? So that's the idea. The energy that it takes to bend or to compress or stretch a string is like the bending energy, or the stretching or compressing energy, basically stuff like that. So the bending energy here is equal to the elastic potential energy, because the elastic potential energy is defined as the bending energy, or the energy required to bend an object. But yeah, there's someone also asked why D for why is D 11. Wait, D is 11.9, or you mean B? Oh, I see. They're asking for D, why original length is 11.9 nanometers. So that's because the original length of the rod, or the original length of the DNA, was 11.9 meters and 9 nanometers, right? Because they were asking about how long is the segment of DNA. The original length of DNA is that 11.9 nanometers that we're interested in. But yeah. Any questions you guys have just generally about this topic? Any concerns or like any issues? Anything that came up in the online or just in general? Or you guys want to like just rant about the exam for the last 4 minutes? Like any questions about the exam? 37. Also, so yeah. So this is 37 degrees. But yeah. I mean, if you guys want to like unmute and talk about the exam, or if you want to use the chat to talk about the exam as well, I have. So today was the homework review session for like this past week stuff. Tomorrow there's going to be an exam review session from 6 to 8 p.m. That's the big one. And then at least the really big one is going to be Tuesday. Amit is the other peer leader. At least he was a former peer leader for physics, and he's a grad student now, but he's going to be helping out. He's going to be there at the MSLC hopefully from 10 a.m. to like when the exam starts, like around 5:45 is probably when we're going to head out. 5:30, 5:45, something like that. I'll be there from 12:20-ish to the same time because I just have class up until 12:15. So I'll head out from Lecture Center C, I think, and be there at 12:20-ish. And so hopefully I'll see some of you guys there on Tuesday. But yeah, there's multiple opportunities to review for the exam tomorrow. There's an exam review session, and Tuesday there's going to be an exam review session. So yeah, if you guys have classes, I'm sorry, but I mean, there's a session in the morning basically with a meet there, and there's also going to be sessions in the afternoon basically. So we haven't quite decided on the structure yet because it's just so difficult to manage, especially like considering the fact that there's probably going to be a lot of students there anyway, with a meet. And so when I come in, it's just going to be like a little bit hectic because he'll be already teaching or the midway through something. And so I'm not sure if we want to split up like every hour, do a topic or do something like that. But my ideal way of preparing for the exam is just go through all the quizzes, review any outstanding or important written homework problems, go over stuff from the online, but like literally just take every hour, hour and a half, focus on a specific chapter. That way, like you can cover all of the important stuff in each chapter and then just not have to like jump around and stuff. But mostly what it seemed like for the last review session that we had is that people just sat there and kind of like asked questions about the exam, like the practice exam that you guys have. And that was just kind of the gist really of what was going on. There was occasionally some stuff about like the written or the online that people asked, but it seemed more like a free drop-in session. So like literally just everyone just going to be studying there. And if you guys have any questions about anything that you've taken or had in the past couple of weeks, whether it be a quiz question, online homework, written homework, practice exam, we're available to answer any questions or explain anything. If I had my way, I would be able to like also do a lecture review, like literally just go over the important concepts and just kind of reteach some certain things, especially like for last week, for people who were in DeJong's class, he didn't really teach the energy subject because he wasn't here. And especially for this week's stuff with the Young's modulus stuff, I would like to have an opportunity to go over that stuff and teach it in a sense, because I mean, not having a teacher and relying on online videos isn't, I guess, optimal, but in the meantime, he does have those online videos that he has, and I that's what we learned off of, because I had 131 during the pandemic, and so yeah, I mean, if you can watch those, they're very, very helpful in my opinion. That's at least where I'm getting like all of my knowledge. And yeah, I mean, I'll see you guys either Sunday, hopefully both Sunday and Tuesday, or one or the other. But yeah, try to make it if you guys need help, and I'll be there, and hopefully we can get some better scores in this next exam. But yeah, that is all, and I will stop the recording, and hopefully you guys have, good rest of your night, and I'll see you either tomorrow or Tuesday or both. Alrighty.